This is the high-level video on efficiency in sorts. So for this, we're just going to go over a few of the efficiency metrics. So there's different things, they're called big O notation. And there's several different types, and they all vary based on efficiency. So the most efficient one is O1, which means no matter how large the list is, it will only take 1 unit of time per list size. So it takes the same amount of time on one list as it does on an 1,000 element list. So things like this would be like swapping an array element. Or it could be something like looking at accessing the index of one element in a list. So, and then there's the next one is ON, which scales with the size of the list. So something like doing a linear search. And then the next one is O log n, and it takes a logarithmic time. So in certain instances, it could be faster than ON or equal even to O1. But most of the time, it's going to be just a tiny bit less efficient than ON. So something like this would be like binary search, where instead of having to go through the entire list, it can just go through a logarithmic amount of the list. And the next one is log n, but it's n log n. And this is used for things like quicksort, where it takes the amount of elements in the list and then it multiplies that by a logarithmic amount of elements in the list. And after this is where it starts to get a bit more inefficient and it starts to really show. So it'd be like O n squared. Now these are things like an sort of like a bit of like an inefficient sort would be O n squared, or it's something that would take basically a large amount of space. Then the next one is O n cubed, which again is just it's basically the same as O n squared, but it takes another element. So it could be like if you were to have 3 nested for loops, where it's going through the same list elements, 3 times and 3 times and 3 times. And then after that is where it's going to be at a rate of 2 to the power of n, which is going to scale like 2, 4, 8, 16, 32, and so on. And this is for where an element is going to take amount of time is going to be 2 to the power of the amount of elements in the list. And then finally there's n factorial, where it's going to take a factorial amount for each element in the list. And this is the most inefficient one. So this could be like you just randomly pick an element out of a hat and until you get the right one, and you keep replacing it every time, where you don't know if you're going to get the element, and every time it kind of starts over. So it could be an infinite amount of times, really. And then there's also sorting methods. And there's different things, they have different efficiencies and different space efficiencies. So there's really 3 factories, where one is the amount of space. So how much data does the sort take? 2 is memory. So how much is it going to take up in RAM? How many processes is it starting? And then 3 is going to be time, or really CPU intensity. So if you have a sort that takes a very long time, it could be very space efficient, but still take a long time to execute. And then there's a few famous sort methods that comply with this. where you can even scale them with these big O notations. So you have, like, the quickest one is quick sort, which is n log n. And then there's merge sort, which can take about n log n time as well, but it can scale all the way up to n squared. And then there's other ones like insert and selection sort. That's basically all you really have to consider when it comes to sorting elements in an array list.